Hello. So today I want to talk about the inverse function theorem. This is essentially answering the question of how does the derivative of a function relate to the derivative of the inverse of that function, right? How when you reflect a function across the line y equals x, how does the slope change? Right? Because remember, that's what I pictured here. Remember a graph of a function, to bring it from the graph of the function to the graph of the inverse function, you reflect across y equals x. Because essentially what we're doing is we're interchanging the x and y axes, right? And the process of taking an inverse interchanges x values with y values, and so it interchanges the x axis with the y axis, and that leaves the line y equals x fixed, right? And then flips everything else across that line as you interchange those axes, right? So the inverse function theorem says that if you want to think about say we have some point, and let's say that point over here, let's call it A, comma, B, right? That would be a point on the graph of F, right? So I'm going to give that a name. So let's call that point A, comma, B, right? And let's say that at that point, let's say we have slope M. Right? Then what does that tell us about the graph of inverse? It tells you that there's going to be a corresponding point over here, right? If you take the perpendicular across y equals x, because it's a reflection. So there's going to be a corresponding point over here, B, comma, A. And what would the slope be at this point? At this point, you would have not a slope of m, but instead a slope of 1 over m. You would take the reciprocal of the slope. How do I know that? Well, you can think about it just visually. It kind of makes sense. Think if that original slope, m, say we're 3, right, over 1 unit, up 3 units. You can see when after you reflect it, now it's going to be something like small positive slope, maybe like slope 1/3, right? But to be a little more rigorous about it, think of it this way. Up on the first line, if you had rise over run, whatever quantity that was, right, the rise is change in y, and the run is change in x. Well, the change in y will become the change in x, and the change in x will become the change in y when you take an inverse function, because you're trading x values with y values, right? So that's why you take the reciprocal of the slope, right? So that's the wordy sort of version of IFT, right? Is you could say when a function is inverted, right? When you invert a function, the slope gets reciprocated, right? This is the core idea of the inverse function theorem. You could say this is, change in y over change in x, right? What happens? Well, you're trading y with x, so you're interchanging the numerator and the denominator. That's why you take a reciprocal to get the new slope. Now, let's make it a little more formal, right? Because that we don't just want a sentence, we want it, stated a little more precisely, a little more mathematically. So to say this more formally, what would we say? We would say that if I want the slope of f inverse, how do I say slope of f inverse? So I'm going to write f inverse prime, right? Slope of f inverse. At what point? Well, at b, right? Look at the graph of f inverse. B is actually the input at which I'm calculating the slope. So if I want the slope of f inverse at b, what is that going to be? It's going to be 1 over the slope of f, right? F prime. Evaluated at what point? Evaluated at a. Because if you look here, the slope of f is being evaluated at the input a. Right? So you have to be a little bit careful, because it's not just that f inverse prime equals 1 over f prime, leaving the inputs the same. It's at 2 different inputs, right? If you're doing f inverse, you're calculating the slope at b, then the original f, you're calculating the slope at a to get this reciprocal and this reciprocal relationship, right? So this is something that we have to be a little bit careful about when you're applying the inverse function theorem. So this would be a valid way to state the inverse function theorem. If you want to make it even more explicit, you could also say the following. You could say that notice that B is actually equal to f of A. So and also another way to say that is that A is equal to F inverse of B, right? So if you want, you can call B the variable X, and then sub in to get that the inverse function theorem becomes a nice little formula. You get F inverse prime of X equals 1 over F prime of F inverse of X. And this is probably the most common way that the inverse function theorem gets stated, right? So what did I do there? I was just saying we already had this statement up here of the inverse function theorem, but I took B and I replaced it by X, right? I took A and I replaced it by F inverse of X. So that's right. That's because that's another way that you could label these points instead of labeling it as A comma B, right? Say this point here, right? This B comma A. You could instead label it as X comma F inverse of X if you want. And so it's the same formula. It's just labeled, instead of labeling it as B comma A, we're labeling it as X comma F inverse of X. But this probably is the most common statement of IFT. But this sometimes it helps, I think, to use it in this form too. To be honest, they're both good ways to write it. So it kind of depends on what information is given. So let's look at this in an example. So here I have kind of a general informal statement, then a slightly more formal statement of it. Let's look at this in a few examples. So here's one nice example of the inverse function theorem. So given, here's a nice short example, given that f of x, let's take the function e to the x, right? Given that f of x is e to the x, and given that we already know the derivative of e to the x, if we take e to the x to be the function that equals its own derivative, or one of a different family of functions that equals its own derivative, but in particular, for e to the x, it is true that that the derivative of e to the x equals itself, right? So given this, let's find the derivative of the natural logarithm right, which is the inverse of e, right? This is the inverse function. If f of x is e to the x, then f inverse is natural log of x. So what could I do here? Well, let me apply this theorem. So what would I have? I would have the f inverse prime of x would equal 1 over f prime. Well, and I should note that this is the derivative of a log, right? Because I'm defining log to be the inverse of e, right? Natural log is the, in this context, this is the definition we're taking of natural log. So what does this become? It becomes 1 over f prime of f inverse of x. Well, what is that? That's 1 over f prime of f inverse of x is just log of x. What is f prime? F prime is e to the x. But here I'm substituting a log of x into f prime of x. So I have the function, see the function f prime is e to the x, but then I'm subbing in a log x for x. Well now the e and log cancel and I end up with 1 over x. There's the derivative of natural log, right? So 1 over x is the derivative of natural log, thanks to the inverse function theorem, given the knowledge that e to the x is its own derivative. Right? So there's IFT applied to a really famous function, right? Applied to e to the x, which lets us get the derivative for log of x. So that's a very famous one. Right, here's another very famous, very important one. Let's find the derivative of the function arctangent using IFT, right? Using the inverse function theorem. So what could I do here? I could say, well, the original function is tangent of x, right? So that the inverse can be called arctan. And the derivative of tangent is secant squared, right? And now the question is, what is the derivative of f inverse? This is where IFT steps in. All right, so I have tangent is f prime, the derivative of tangent, secant squared. F inverse is arctan, and I want f prime inverse, right? So this is my calculation now. So I'm going to say, okay, what's the derivative of arctan? Well, that's my f inverse, which by inverse function theorem, I can say is 1 over f prime of f inverse of x. So what is this? If I remember, f prime is secant squared, right? But now it's going to be secant squared with what subbed in? With f inverse subbed in. Well, that's arctangent, right? So sub in arctangent for f inverse. Great. What does this become then? You could just leave it there. That's not an incorrect formula for the derivative of arctangent, 1 over secant squared of arctangent of x, but it can be simplified, right? Because arctangent, what does this mean? This, a nice way to think of arctangent is you think of the angle whose tangent is x, right? Is a good way to say arctangent, or the arc on the unit circle whose tangent is x. It's called arctangent, right? So you can represent this as a geometric diagram, right? Tangent is opposite over adjacent. So you can say that this is represented, the angle arctan of x, if that's my angle, then opposite over adjacent must be x. So the sides, the opposite and adjacent side of that triangle must be in a ratio of x to 1, right? X is the same as x to 1. So there was no denominator, so I just threw in a 1. Then I could use the Pythagorean theorem to find the hypotenuse. There's the hypotenuse. And then I could calculate a secant, right? What is secant? The secant of this angle, arctan of x. Well, secant is the reciprocal of cosine. So secant is hypotenuse over adjacent, right? So the secant is actually square root of 1 plus x squared over 1. And the over 1 doesn't do anything, right? So now I can calculate that secant. So that secant is just root 1 plus x squared. But it wasn't just secant, it was secant squared, right? Therefore, the square root and the square cancel, and I get the derivative of arctangent, which is a surprisingly clean result, right? The derivative of arctangent is 1 over 1 plus x squared. So there's our derivative of arctangent, again, using the inverse function theorem. Right? So these are some famous functions that we can calculate their derivatives using the derivatives of their inverses using the inverse function theorem, right? E to the x, an exponential function, tangent of x, a trig function, right? Now, I want to also look at an example that is not famous, right? Just sort of an ugly random function that we can still say something about it using the inverse function theorem, right? Even though it's not a famous one, it's not one that we have a nice formula for the inverse for. So consider this function. Say we have f of x equal, let's say it's x to the 5 plus x plus 1, right? And suppose here I said find the slope of the inverse of this function, find the slope, and I want to find it at the point 1, right? That's my goal here, right? So first of all, I want to notice that the inverse to this function does exist, this f of x, right? Even though I have no idea how you would find a formula for this, right? Imagine what's the standard method in pre-calculus for finding a formula for an inverse? how do you find a formula for F inverse? You would take an equation and then you swap X with Y, right? So you interchange the X's and Y's, and then you solve for Y, right? This is the standard method for finding an inverse function, but I have no idea how I would solve this degree 5 polynomial for Y. Good luck getting that as Y equals some expression in X, right? It's not going to happen, at least for me, right? It's not going to happen. So, and in general, there's no algorithm to do that with a degree 5 polynomial. This particular degree 5 polynomial, maybe there's a way to do it, but it's not immediately apparent to me if there is. So, so this is it's not something that we can do by just finding a formula for F inverse and then differentiating using standard techniques, right? Product rule, quotient rule, chain rule, whatever, right? Power rule. It's not gonna happen that way. So instead, here's what we can do. We can say, well, let me instead think about this. Oh yeah, but I should mention the inverse does exist, right? Because if you graph this function f of x, it's going to look something like this. Is the graph of f of x. In particular, it's always increasing, right? It's definitely a one-to-one function, right? And this isn't really part of how we would solve the problem, but it's commentary that the problem makes sense, right? The inverse function definitely exists. This is a one-to-one, right? F is a one-to-one and thus invertible function, because it's always increasing. Why do I know it's always increasing? Well, I know it's always increasing because the derivative is x to the fourth plus 1 is always positive for all x, right? In fact, it's always 1 or greater for all x, right? So the minimum slope of this function is actually slope 1, occurs right here, right? This would be slope 1 of this. For this function, right? When x is 0, it's slope 1. Everywhere else, it's actually steeper, right? This is slope greater than 1, right? This is slope greater than 1, right? So this function has positive slope on the whole real number line. So I know it's invertible, but I have no idea what the formula is for the inverse, right? So now the question is, how can I get this quantity? I claim if this isn't a garbage question, I'm claiming this is somehow computable, right? To find the, oh, sorry, not just the value, but the derivative, find the slope at 1, right? For the slope of the inverse at 1. So here's what you can do. You can, even though we can't find a formula, for a general formula for the inverse, you can still try to invert a particular point by just looking at the desired output, right? So here I'm dealing with f inverse at 1. So if I'm looking at what x value has f of x equal to 1, well, this I could, even though I can't solve the equation in general, I could solve this by inspection. Meaning, well, I want x to the fifth plus x plus 1 to equal 1. So what should I set x equal to? 0, right? So f, because then those first two terms go away. So here, yes, I'm depending heavily on the fact that I picked a clean input, right, where you could kind of eyeball the what x value you would need, right? But so I have that f of 0 equals 1. So that's equivalent to saying that f inverse of 1 equals 0, right? An inverse function interchanges the x and the y. It interchanges the roles of input and output. So I know that f inverse of 1 equals 0. Well, I claim now I actually have all I need to use the inverse function theorem and to get the slope of f inverse at 1. And in particular, what I can do is I can say by IFT, I have f inverse prime at 1, the quantity of interest, is 1 over f prime of f inverse at 1, right? And I just calculated f inverse at 1, that's 0, right? So now I need 1 over f prime at 0. Well, and I already had a formula for f prime up here, right? X to the fourth plus 1. So this is 1 over 0 to the fourth plus 1 is 1 over 1 is 1. So there we go. The slope of the inverse function at 1 is 1, right? And if you look here, that would correspond to, on the graph, here would be our y equals x line. And then the graph of the inverse would look like this, would be the graph of f inverse. And this point here would be the point 0, 1 on the graph of f, which would correspond to this point 1, 0 on the graph of f inverse. And since I had slope 1 over here, it would actually still be slope 1 over here. Slope 1 is the one slope that it's its own reciprocal, well, or negative one, right? Slope 1 and -1, they actually equal their own reciprocal, so they stay the same slope when you reflect them across the axis, the y equals x, right? The line y equals x. So you get slope 1 at 0, 1 for f. You get slope 1 at 1, 0 for f inverse. Right? So there we go. So we have two famous functions where we applied IFT to the exponential function, to a trig function, right? We also applied it to just some random ugly degree 5 polynomial, right? But it works just fine in all of these cases. So great, thank you. There is our inverse function theorem.